The next programme for this course stays underwater to see how scientists are trying to unravel the biology of the herring. That's Listening in the Dark at the same time, 2 weeks from today. Later this morning at 5 to 10, the Science Foundation course follows the daily balancing act performed by our bodies in matching energy use and intake when it takes a look at a day in the life. But first, the Materials in Action course continues the story of the development of a new design of car engine. Cast in the Right Mould sees how materials were chosen for particular components.
This Rover K-Series engine contains hundreds of components. Decisions involving material selection and process choice will have been made for each one of them. Clearly, both the geometry and function of a component will strongly influence these decisions. To illustrate this, we are going to look in detail at the manufacture of two of the major components in this engine, the crankshaft and the cylinder block. Both are made using innovative casting processes and involve a change of material from that traditionally used. We will start by considering crankshafts. Traditionally, these have been produced by closed-die forging on large presses. This press can produce a continuous force of up to 6,000 tons. Such machines are expensive and can only be afforded due to their low cycle time. You can see here the high throughput of the process. The medium carbon low alloy steel enters the process as billets that have been accurately cropped from a length of rolled bar. They are then heated to the forging temperature of 1260 degrees centigrade in an induction heater. Next they go by conveyor to a preforming press, which rounds off the corners of the billet. This is done to prevent excessive wear in the main forging dies. They are then transferred to the main press. The forging takes place in two stages. The preformed billet is forged in an impression die and a finishing die in quick succession. A graphite-based lubricant is sprayed onto the dies. This both lubricates and cools the mould surfaces. The high forming rates employed ensure that the component spends little time in contact with the tooling, so that no reheating is necessary between the various stages of the forging operation. Forging is then transferred to a clipping press, where the excess metal, the flash, is removed. The flash is simply sheared away from the crankshaft in a set of dies. You can see that the amount of material in the flash is substantial. It can be up to 10% of the weight of the component. Finally, the crankshaft is straightened in a hot set press. This removes any distortion and ensures that the final dimensions of the crankshafts are correct. Low alloy steel crankshafts then have to be hardened by quenching and tempering to achieve the strength required for service. A major advantage of forging is the form and texture produced in the component. We have sectioned and etched this forged crankshaft so that we can see the forming texture. A forming texture typically has two components, a crystallographic texture and a fibre texture. The crystallographic texture involves preferred orientation of the grains within the component and is difficult to image directly. What is revealed by etching here is the fibre texture. The inclusions have been aligned preferentially along the principal direction of working. This produces a fibrous structure which has anisotropic properties. It is tough and ductile along the fibre direction, but less so perpendicular to it. The elongated grain structure that exists after forging is effectively destroyed by quenching and tempering, as can be seen in this etched microsection. The grey manganese sulfide inclusions are aligned along the direction of working, but the alignment of the grain structure has been destroyed when the crankshaft was quenched to form martensite. The microstructural advantages of forging made it a favoured choice of crankshafts for many years. However, these crankshafts entering a machining line at Rover are cast out of spheroidal graphite cast iron, often called SG iron. I asked Jeff Key how these were produced.
For casting, we use a shell moulding process. This process involves producing two shell halves split along a longitudinal direction. The shell halves are produced from a mixture of sand and a thermosetting resin binder, this being placed against a hot pattern. The two halves then put together and put into a flask into which shot is used as a backup material to hold the weight of the hot metal. The hot metal is then introduced into the mould.
Shell moulding is an unusual variant of sand casting. Metal is cast into a mould made up of two thin resin-bonded sand shells. Each half of the shell is made on a metal pattern plate. A heated pattern is placed on top of a dump box, which contains a mixture of fine sand and a thermosetting resin. The dump box is then inverted so that the pattern is covered with the sand-resin mixture. The resin sets so that the pattern becomes covered with a thin shell of sand, typically 6 to 10 millimeter thick. The pattern plate is then moved with the shell still adhering to it into an oven where it is further heated to fully cure it. The shell is then stripped from the pattern plate using built-in ejector pins. Two shells are then joined together using a thermosetting adhesive to form the mould. Cores are difficult to locate in shell moulding, but this is no problem in this case, as crankshafts are simple 3D solid components. The thin shell is now put into an iron casting box and supported with a suitable granular backing material. Shell moulds can be backed with loose sand, but the SG iron that will be used here expands on solidification due to the formation of graphite. This expansion exerts large stresses on the shell mould, and a stiff, strong backing material is needed if a high-precision product is to be produced. So steel shot is used to back the shell mould. It is first loosely poured in, and the casting box is then vibrated to pack the steel shot down. Once compacted, it is sufficiently rigid to withstand the large stresses created by the expansion of the SG iron on solidification. The mould is now ready to be filled with molten metal. Control of the quality of the molten metal is vital. It is prepared by adding controlled amounts of the necessary elements to a charge of molten steel scrap. Once the correct composition has been obtained, it is transferred to a large holding furnace. This furnace can hold up to 40 tons of cast iron at a temperature of 1480 degrees centigrade. The molten cast iron is transferred to the casting ladles via an intermediate ladle. It is at this stage that the relatively volatile magnesium additions that spherodize the graphite are added. The stirring that occurs when transferring the molten metal to the casting ladle ensures that a homogeneous melt is produced. The metal is then poured from these more manageable casting ladles into the moulds. The rate of metal flow is controlled so that a constant head of metal is maintained in the running system. Although an even, controlled fill rate is essential, SG iron is a relatively forgiving casting alloy when compared to, say, aluminium or magnesium alloys. This is because it does not form a particularly tenacious oxide and expands on solidification. Once the mould is full of metal, it carries on down the line to cool. The line is convoluted here to allow the casting more time to solidify. You can see as we move down the line that the temperature of the casting gradually decreases. As with sand casting, relatively little of the heat coming out of the casting is lost directly to the environment. Most of it is absorbed into the shell and the surrounding shot. One advantageous side effect of this is that the heat breaks down the thermosetting resin, so that the casting can easily be removed from the mould. After about 40 minutes, the casting box is simply inverted, and the steel shot and the now decomposed resin-bonded shell empties onto a coarse grill. This catches the casting, which is transferred to a cooling conveyor. The casting box moves along the line to be filled with another shell mould. 3 crankshafts are connected to a single running and feeding system, so that each casting box produces 3 components. Each casting is now cooled in air on this continuous conveyor for 65 minutes. The casting is shot blasted to remove any sand or resin sticking to it. It also gives the crankshaft a much more pleasing appearance. Finally, the running and feeding system is removed from the casting, and each crankshaft is hand finished to remove any unwanted material or flash. This is a very efficient foundry, and it only takes 4.5 hours for a crankshaft to be produced from pouring to dispatch. This enables high production rates, up to 1,000 an hour to be produced. Although this foundry makes mainly crankshafts, over 2 million a year, the plant is relatively flexible, and other components could be made simply by changing the shell moulds. Indeed, crankshafts for a number of different engines and manufacturers are cast fully interchangeably in this foundry, with only the mould pattern changing. Of course, cast SG iron has a distinctly different microstructure to that of forged low alloy steel. For a start, there is no forming texture. Here we see an etched macro section of an SG iron crankshaft. Very little structure can be seen, and whilst this means that the properties of the component are more homogeneous, the final product is less strong than the forged crankshaft. However, the mechanical properties of SG iron are good when compared with other cast irons. The addition of magnesium changes the graphite from the flake form found in grey iron to the spheroidal form shown here. Spheroidal graphite is a smaller microstructural stress concentrator than flake graphite, which tends to easily initiate cracks in grey iron. This means that SG iron is much tougher. The strength comes from the nearly fully pearlitic structure of the matrix. The spheroidal graphite can be seen here to be principally surrounded by pearlite. Lamella, ferrite and cementite can be seen in several areas. Clearly, whether a casting or forging route is chosen, some secondary machining will be necessary to obtain the precision and surface texture needed for service. I asked Jeff Key whether the amount of secondary machining varied between forged and cast crankshafts.
Certainly, the machining processes are very much the same, but the shell moulding process produces a very accurate casting, and therefore we need less machining allowances. Also, on the forged crankshaft, we need to machine the web to get into the journal. This is not necessary, as can be seen here, on the cast crankshaft.
So you've decided to use cast crankshafts for the K-series engine. Is it the case that cast crankshafts will be used for all such engines in the future?
The general trend for passenger vehicles is towards cast crankshafts. Now, for K-series, the move towards the cast route was accompanied by an increase in number of bearing journals. As we can see here, there are 5 journals as against the 3 journals on the A-series forged crankshaft. Now, this permits lower stresses on the crankshaft, and therefore we can use the lower strength iron rather than the steel. Diesel engines and high-performance vehicles do have high stresses in the crankshaft. Therefore, currently, they still need a forged crankshaft.
So although for this engine, a cast iron crankshaft was the most economical choice, a more highly stressed derivative may still require a forged crankshaft. The precise material and process selection depends highly on the function of the component. Of course, this is also true for the second major component we are going to examine, the cylinder block. The main difference when comparing this component with the crankshaft we have just looked at is that with such a complex product, only casting processes are likely to provide viable manufacturing routes. With this in mind, I asked Steve Calvert how had cylinder blocks traditionally been made within the Rover Group.
We've made them in cast iron traditionally. It's a straightforward material to work with, it's easy to procure and cheap to manufacture with. However, with the demands on our manufacturing and design for a much more modern power unit, which the K series is, we felt we had to move to aluminium, which produces a much lighter structure and gives us better weight characteristics in the finished engine.
Having decided on the material, how do you choose the process?
Well, aluminium, unfortunately for the manufacturing people amongst us, is very difficult to work with. It oxidizes readily. It has a long freezing range in the alloy that we use on this material. It picks up hydrogen readily and gives rise to gas porosity. And so from a manufacturing viewpoint, it is very difficult to work with. However, there are a number of functional features which aluminium really surpasses everything else, and in particular its specific gravity. The density of the material is better, lighter than anything that is normally used in engine manufacture. So we were left with casting aluminium, and we looked at three particular methods, basically evolving around die casting and sand casting as well. And our final decision was influenced very much by the final requirements placed on us by designs. They were looking for a product which was extremely demanding in its performance. We set ourselves the highest standards in a world-class sense for the engine, and the manufacturing technology was developed to suit. So, for instance, with this block here, we have a combination of thin walls between the cylinder bores, for instance. The detail which is applied to the casting produce the lightest casting with the required strength in it, and that necessitated us in us developing some novel manufacturing solutions, and in particular the use of pumps and pumping to displace metal from a liquid reservoir into the mould itself.
Could you tell me what is special about the casting process that you use?
The casting process we use is fairly straightforward in terms of the moulding methods we use. We produce a cavity in a block of sand, a hard block of sand, through the use of cold box core manufacture and assembly methods. Where we perhaps deviate from most other casting methods is that we apply an electromagnetic force to a molten stream of aluminium, which is then used to displace that metal into the cast mould from its base to its top under very controlled and very reproducible conditions. And that's important in terms of controlling turbulence and controlling the heat and fluid flow distribution through the casting to allow us to optimize the design against the constraints of using aluminium.
This is the heart of the Rover low-pressure casting process. Liquid aluminium is pumped upwards into sand moulds in these machines. But it's worth quickly reviewing how both metal and mould get to this stage. The sand is stored in these large hoppers. After being mixed with a thermoset in resin, it is transferred to the relevant core-making machine. The sand is forced into a die similar to that used in pressure die casting or injection moulding. The thermoset in resin is then cured, not by heat as was the case in shell moulding, but by passing an amine gas through the sand. This reacts with the resin, forming a hard sand core. This cold curing process enables lower cost mould materials to be used. The core being produced here is the one that produces the cylinders within the block. This core is assembled with others to produce the casting mould. Of course, this casting mould contains the cavity which when it is full of metal will form the cylinder block. From the core assembly area, completed moulds are transferred to the casting machines. The aluminium alloy is brought in as ingots and is melted in electric holding furnaces. The alloy is a precipitation hardening grade, and although based on aluminium silicon, it is relatively far from the eutectic composition. This means that it is a long freezing range alloy. The moulds and the molten metal meet at the casting machine. The moulds are loaded into one of 8 machines, each of which has 2 casting heads. The mould is moved over the tun dish containing the molten metal. However, there is relatively little to see, particularly when compared to shell casting. So it is worth considering what is happening inside the machine. In low-pressure sand casting, molten metal is held in a tun dish. Once the mould is in place, molten metal is pumped upwards. This produces a relatively slow, non-turbulent upward fill of the mould. Pumping continues even after the mould is full. This maintains pressure within the casting until the runners at the bottom of the casting freeze. When the runners are fully solidified, the pump stops and the level of the molten metal drops back into the tun dish. This is all you can actually see as the mould fills with molten metal. As soon as the feeders have solidified, the mould is removed and the rest of the casting solidifies as it is transferred away from the casting machine. The heat given out by the casting as it solidifies is absorbed by the sand, so that little of it is transferred into the surrounding environment. Indeed, it is used to good purpose, since as the mould heats up, so the thermoset in resin that holds the sand together starts to break down. This process is completed when the moulds containing the now solidified castings are passed through a furnace that both solution treats the castings and further breaks down the resin in the sand so that it can be recovered and recycled. After quenching and aging, the runners and feeders are removed and the casting is ready for shot blasting. Again, the shot blasting considerably improves the surface appearance of the component, as well as removing any remaining mould material. The use of an aluminium block has clearly produced benefits in this engine, and this has necessitated Rover developing the low-pressure sand casting process. Aluminium is relatively difficult to cast, and the process control necessary to produce these cylinder blocks can be contrasted to that needed to successfully cast the more forgiving SG iron as crankshafts. With this in mind, I finally asked Steve Calvert if he thought this was the end of the line for cast iron cylinder blocks.
It's certainly the case that a lot of engine manufacture these days, certainly in Japan and increasingly in Europe, are starting to use aluminium materials to a greater degree in cylinder head and block production. However, I wouldn't say that cast iron is dead as a material. It still offers significant commercial advantages, if I can put it like that, in that it is cheap to procure and relatively easy to use in the foundry. All I would say to that is that at any given point in time, a design calls for a certain function and a certain functionality in the product and in the material that you use, and if that dictates that aluminium is used or cast iron is used, then we as foundrymen can equally well address those two materials.